on branch prediction. This is one of the very interesting parts of the machine, the machines that are in your computers. Especially if you have an Android and Samsung phone, it actually employs machine learning algorithms to use branch prediction. Or if you have an AMD machine, it actually employs machine learning for branch prediction, and we're going to build up to that. It's very interesting. It's a very hot area, again, because it's a very hard problem. Okay, so hopefully you're doing the readings. These are the readings that you should have done a long time ago. If you haven't, please do. They're all required. And if you don't recall what branch prediction is, we were talking about how to handle control dependencies. Basically, you want to keep the pipeline full in a machine when you have control flow. And the question is, how do we actually keep the pipeline full? And we were looking at this solution in particular, guess the next fetch address. If you have time today, I'm going to cover some of the other solutions briefly also, but this is the solution that has been employed predominantly in all computers today. Okay, and recall this picture. This is the front end or fetch stage of a machine. We enhanced it with two prediction structures. One is a cache of target addresses that tells you what is the target address of the branch based on previous executions, and you index it with the program counter address of the current instruction that you're fetching. And this tells you, oh, this is the target address of that instruction. And if you get a target address over here, you implicitly know that this is a branch. And you also index another structure that basically tells you what should the direction prediction be for that particular branch, meaning that where does the predictor expect this branch to take the control flow to? Is it the target address, or is it the next instruction, which is also called the fall-through instruction? So if this says taken, you basically use the target address coming from the BTB as the next fetch address. Otherwise, you use PC plus instruction size. So you somehow need to know the instruction size clearly, which we briefly discussed. Okay, so and then we were talking about how to do this direction prediction, right? And then we discussed a bunch of compile time mechanisms, meaning somebody tells you this direction prediction by encoding a bit in the instruction set architecture so that you don't need to index a structure, but you get that bit somehow, which we discussed also briefly. And we said that these techniques are not adaptive to the runtime branch behavior because you can encode only a single direction with these, whereas if a branch changes behavior while it's executing, for example, a loop branch, sometimes it's taken, sometimes it's not taken, depending on how many iterations you have in the loop. Or a branch that's testing a condition. If X is true, do this, otherwise do that. X may be true or not true, depending on dynamic instances of X, right, of that variable. If you're testing a bunch of variables in an array, for example, if you have a 1,000,000 entry array, if you're checking if each of the elements of the array is equal to 0, it's probably going to be very dynamic, depending on the array that you fed into the program, right? If the array has a lot of random numbers, you will probably get the branch to behave randomly. But if the array has all zeros, then the branch that's testing whether each element is equal to 0 is always going to be taken, right? It's only going to go into a single direction. If the array has half of its zeros and half of it's greater than zeros, then the branch will be taken in the first half when it's testing the first half of the elements in the array, and it will not be taken in the remaining half. So this is an example of a branch that shows very dynamic behavior because it's really checking whether a data element is equal to or greater than or less than something, and that data element is dependent on what somebody fed into the program. And there could be many, many arrays, as you can imagine, right? If you're doing matrix multiplication, for example, the branches that you have will behave very differently. As a result, we said that runtime behavior should be taken into account in branch prediction so that we can get higher accuracy. And we discussed one particular example of a dynamic branch predictor, last time prediction. And we're going to see many, many more sophisticated examples in this lecture. So this is, again, we discussed this. Last time predictor, what does it mean? This means that you remember the direction the branch took last time it was executed. Was it taken or was it last taken? Was it not taken? And basically, the machine, when it fetches the branch again, based on this memory, it decides, okay, I'm going to do the same thing I did last time I executed this branch in the machine. So if you see the same program counter, you decide what you did last time, and you basically do the same thing. So if the branch was taken the last time, you predict that it's going to be taken again. That's the idea. So that single bit per branch that's stored in the branch target buffer indicates which direction the branch went last time it was executed. you update that bit when the branch finishes execution. And in the fetch engine, whenever you see the program counter of the branch again, you get that bit, check. If it says taken, you predict the branch has taken. So if a branch has this sort of behavior, meaning that it's taken the first 10 times, and it's not taken the next 10 times, then this is, you actually predict this with 90% accuracy, as we discussed last time. Why you predict all of these correctly, except when you actually change direction over here. This is the 11th instance of the branch. You predict it to be taken because the previous instance was taken, but it turns out it's not taken actually, so you mispredict once. And then you mispredict, assuming that this is executed in a loop, if you remember. If this is executed in a loop, the branch changes direction again when it switches from not taken to taken. And at that point, you predict this instance of the branch as not taken because the previous instance was not taken, but you're wrong because this is supposed to be taken, the branch changed behavior. So if you remember just last time what you did for that branch, with this sort of pattern, you get 90% accuracy, which is much better than the accuracy that you would get if you have a single bit provided by the compiler or the programmer saying the branch should be predicted as taken or not taken, because with that kind of prediction mechanism, you're only 50% correct, right? You can only encode that information with a single bit. Here, you're changing the single bit every time you execute the branch, assuming that the direction is changing. Okay, so hopefully this is clear, right? It's basically last time prediction. Do what you did last time. People use this also, right? Whenever you face a situation that you did something about before, maybe the first strategy is to do the same thing that you did last time to deal with that situation. It may or may not be a good strategy, but if the strategy works every time, maybe that's a good strategy, right? That's the idea over here. That's very similar to how humans behave. Of course, there's a downside. If you do this sort of thing, you always mispredict. You're guaranteed to mispredict the last iteration and the first iteration of a loop branch. So, for now, ignore the remaining ends over here. If you look at a loop branch is taken 10 times, and the 11th iteration is not taken. Basically, it's a loop that executes 11 times, let's say. And if you keep looping this way, then you're going to mispredict the last iteration of the loop, because you think that the loop is going to be executed based on the previous iteration. And then when you get into the first iteration, you're going to mispredict this iteration of the loop also, because what happens is the last time the branch was executed, it was not taken, but it's supposed to be taken when you get into the loop. So basically, if you have a loop with n iteration, you are guaranteed to mispredict twice, and so your accuracy is n minus 2 over n. Now, if n is very large, this is not a problem, probably. If a loop iterates 1 billion times, basically you're almost 100% accurate. But if a loop iterates only twice or once, basically you have a problem. Well, once means you execute the loop branch twice, actually. So loop branches for loops with large number of n, you have it's good. But loop branches for loops with small n, meaning number of iterations, you get 0% accuracy. It's a loop that is taken only once. You execute the branch twice, essentially, in this case, and you get 0% accuracy because the last time, the current direction of the branch is always the exact opposite of the last direction. The direction the branch took the last time it was executed. So you can think of these as patterns like this also. How do you predict these patterns, in a sense? If a branch basically has this behavior, taken, not taken, taken, not taken, last time prediction clearly will not work. Exactly. In fact, if you know this, you should really do exactly the opposite of what you did last time, right? Yes?
Wouldn't that only be an issue if we have nested loops? Because if a loop is just called once, we would still have the 90% accuracy.
That's right, exactly. So I'm assuming that you have a nested loop. Yeah, basically, you have a loop, you iterate once, and then you come back to it at some point, and you execute the branch, and then you come back to it again, and then come back to it again. Most programs actually have that sort of behavior. The assumption over here was also the same, actually. You keep coming back to execute that branch over and over. Okay, so we're going to improve on this, and we'll see the advantage and disadvantage in a little bit. But how do you implement this? It's actually very simple. So this is our branch address program counter, and this is our branch target buffer. So I'm going into a little bit more detail. We're going to see memories later on even more. But basically, this is, you index the branch target buffer with some bits from the program counter, and you basically check if the branch program counter matches. So you actually have a tag over here. This is similar to a cache that we will see later on. Basically, you check if this program counter is associated with an entry, a target address in the BTB. That's how you index the BTB. So we're adding only a single bit over here saying that what was the direction this branch took last time it was executed. And whenever you execute the branch, you update this bit. And the prediction now is basically, I already said this over here. The prediction now is if you actually have a hit in the branch target buffer, you get this bit saying what was the direction last time the branch was executed. If it's taken, then you predict the target address to be the next program counter to fetch from. Otherwise, you predict PC plus 4 or PC plus instruction size. Basically, that's how we change the logic element. You can think of this also as a direction predictor. What we're doing over here is, if you go back to this picture, we're embedding this direction predictor into the BTB. Make sense? Because both the direction predictor and the BTB, if we go back again, use the program counter as an indexing mechanism. Basically, the direction predictor gives you a taken or not taken bit based on the program counter. The BTB gives you the target address based on the program counter. Okay. So you can also think of this as a state machine. You know about state machines really well. Basically, we have, for each branch in the branch target buffer entry, we have a state machine, a single bit state machine that again encode two states. One state is predict not taken state, and the other state is predict taken state. And if the branch is actually taken, you basically stay in the state, predict taken state, the last time it was executed if it's actually taken. If the branch was actually not taken the last time it was executed, then you go back from predict taken state to predict not taken state, assuming you were in the predict taken state to begin with. And if you're in the state to begin with, and if the branch was actually not taken, you stay in the state because your prediction was correct. And if your prediction was not taken and the branch turned out to be actually taken in the execution, you change the bit to predict taken state. Basically, you have a state machine, and you basically change the prediction state based on the outcome of the branch that you've seen for the last time. That's why it's a last time prediction. Right. Okay, so hopefully this is clear. This is the basic, very simple prediction. So one of the problems is, it turns out this works not so bad, but we're going to see there are downsides and there are much better prediction mechanisms. So one of the problems with this prediction mechanism is it's a last time predictor basically changes its mind too quickly. So basically, whenever you see one offending outcome, offending meaning that different outcome than last time, you basically change the prediction state. You move from here to here or here to here if the branch is actually not corresponding to your prediction. This may not be a good thing in all cases. Actually, in most cases, it's not a good thing. As you've seen with the taken, not taken, taken, not taken, taken, not taken, taken, not taken behavior, right? So you don't want to do this even though the branch may be mostly taken or mostly not taken. Basically, this is done even though that's the case. So the solution idea here people have developed, and this is very effective. This was the state of the art for a really long time in computer architecture, at least for a decade. People added hysteresis to the predictor so that the prediction does not change on a single different outcome. So what's hysteresis? Hysteresis is basically some inertia that you add to the system so that the system doesn't change its state very quickly. You may notice this in, for example, air conditioning or heating systems. Usually people, whenever they detect temperature and they want to take an action based on a temperature, they add some hysteresis. For example, if you want to set the room temperature to 22 degrees Celsius, let's say, and if you have a temperature sensor that basically detects and controls heating or cooling so that you can stay at 22 degrees Celsius, you want that temperature you want the control system to have some hysteresis. Why? Because let's assume that you're exactly at 22 degrees Celsius at that point. Let's assume that you're cooling the system. And once you start cooling the system, it'll go down to, I don't know, 19.999, 21.999 degrees Celsius, right? If at that point, the heating system kicks in and starts heating the room, then you go into the heating mode, and then the heating mode increases the temperature, and you get to 22.0001 degrees Celsius. Right? At that point, cooling system kicks in, and you go back to the temperature that's lower than 22 degrees. At that point, heating system kicks in. So you have a problem oscillating, right? There's a problem of oscillation if you change your mind too quickly after you make a decision. So usually these systems are designed such that you have a buffer. The heating or cooling system doesn't kick in until you actually go below a threshold. You don't change your mind so quickly at the threshold value. So maybe you say, only after the temperature reaches 21.2 degrees Celsius, I'm going to start heating the room. But if it's between 21.2 or 22, I'm not going to start heating the room because I may go into this oscillation mode. So you basically look for more evidence as to the fact that temperature is actually decreasing. Make sense? That's true for the cooling as well, right? If you don't quickly start cooling the room, if you're just see one evidence that temperature is increasing to 22.01, you wait until 22.8 degrees, for example. At that point, you say, okay, I have enough evidence that the temperature is really increasing. Now I'm going to go into the cooling mode. So that's a very good example of hysteresis. And we want to do exactly the same thing in the systems that we build that make this sort of decisions. So how do you actually add hysteresis into the system? Basically, look for more evidence. What is the evidence? In this case, don't change your mind in a single opposing outcome, but use 2 bits to keep track of the history of predictions for a branch instead of a single bit. Look for, let's say, 2 offending outcomes. If you predicted not taken, and if you're in the not taken predict not taken state, wait for 2 cases where the branch is actually taken so that you change your mind and say, okay, this branch should be predicted taken next time. And that's the idea. The way you add hysteresis, collect more information. Now you can actually have 2 states for taken and 2 states for not taken instead of 1 state for each. And this was introduced in the seminal paper that was written by Jim Smith in 1981. And that became the state of the art very quickly in modern machines. So basically, what does it mean? Each branch is associated now with a 2-bit counter as opposed to a single-bit counter. 1 more bit provides hysteresis. A strong prediction does not change with a single different outcome. You have to wait for 2 different outcomes. And you can imagine extending this to 3-bit counters, right? A strong prediction doesn't change after n outcomes. But, and people have just looked at the space. But let's take a look at what's used a lot. So this is a 2-bit counter state machine. So these are the states that encode predicted taken. So if the branch is in this state, 1, 1, then you predict the branch to be taken. And these actually use what is called saturating arithmetic, basic arithmetic with maximum and minimum values. You basically saturate at 1, 1 or saturate at 0, 0. Now, what does that mean? So these are the predicted taken state. These are the predicted not taken states. If the branch is predicted taken, and if you find out later that it's actually taken after you execute the branch, you stay in the state. That's the saturation. This is also called a strongly taken state. If the branch is predicted taken, and you find out that you mispredicted, meaning that when you execute the branch, it's actually not taken, then you move from this strongly taken state to this still predicted taken state, but it's weakly predicted taken state. I'll call it weakly. You'll see that later on. You will still predict the branch taken next time, but now you're less confident about it because you moved from the strong state to a weak state. Now, at this point, if the branch, you again predict the branch taken, if it's actually not taken, then you change your mind. Then you go into this red state where you're going to predict the branch as not taken next time, right? So we've added some hysteresis. The same movement happens from here to here, basically to be able to change. Here at this point, you're thinking that the branch is strongly predicted to be not taken. What it will take you to change your mind is to see 2 different outcomes that are actually taken, right? So only by going through these 2 outcomes, you go into a predicted taken state. So you don't change your mind quickly between 2 states. That's the idea. Only at this point you change your mind quickly, so you're at the boundary still. Maybe there are some other solutions to that. But we've solved the problem of changing your mind with a single opposing outcome. Okay? So hopefully this is clear. And these are basically showing different paths. So basically, if you're predicted taken, to be able to go from this state to this state, you actually need to see 2 opposing outcomes. But if you don't see the 2 opposing outcomes, for example, if you see 1 opposing outcome, you're predicting it taken, and the branch is actually not taken. In the next instance, you're going to predict the branch taken, and if it's actually taken, you save the misprediction compared to the last time predictor because you predicted it taken, and it's actually taken, and you go back to the strongly taken state. So basically, whenever you see an outcome that corresponds to your prediction, you make the prediction stronger the next time. Whenever you see an outcome that doesn't correspond to your prediction, you make the prediction weaker for the next time by changing states. And this is the only place where actually, this is the only place where you actually transition. Okay. Okay. So, okay, I've already said this weakly taken, strongly taken over here. Okay, so if you actually do this, then you have a big gain in this sort of branches. If your branch shows behavior like this, taken, not taken, taken, not taken, taken, not taken, that's different every single time, you still get 50% accuracy in this case. Why? Because let's assume that you start with weakly taken. It works for strongly taken also in this case. Your initial value matters in this case. Basically, you start with weakly taken, then you get 50% accuracy, because you only mispredict the not taken cases over here. We will see that you will do better in these cases. So now accuracy for a loop with n iterations becomes n minus 1 over n. Why? Because you only change your mind at two opposing outcomes. Yes? Go ahead.
Do we change immediately to the strong prediction or not? Because if we get stuck between the two weak ones and it keeps changing,
that's it.
There's no accuracy whatsoever.
Yeah, exactly. So you can still get into these bad cases, basically, but the idea is that hopefully those bad cases are reduced in this case. But people have looked at different ways of building these state machines, different transitions between these different states. Well, we're not going to get into that. You can optimize. And it's very much dependent on branch behavior. Yes?
Possible to construct an example that will get zero accuracy for every kind of prediction?
For every kind of prediction.
Like, to just construct an example that does that?
I'll encourage you to do that, sure. I think you can, yes. I think in the worst case, all of these branch predictors can run into these situations where they mispredict.
Intentionally being mean to the computer?
Yeah, potentially, yes. But that's a good way of thinking in designing machines, yes. What is the worst case performance? But we're not talking about worst case performance here. Okay, so overall, on the average case, you get better prediction accuracy with this, because as you see, you get 50% here, which we couldn't before, but the downside is more hardware cost. Now you actually have another bit in the counter. And if you actually want to add more hysteresis, you have 3 bits in the counter, and you have maybe complex update mechanisms for that state machine. We're basically adding a state machine per branch. Okay. But of course, counter can be part of a BTB entry. That's true. Okay, so this actually leads to, let's say, 80%, 85% accuracy. It turns out in some programs this leads to 90% accuracy. It depends on the program. This is also called bimodal prediction, which is an unfortunate name. I don't know what that means. Anyway, I like 2-bit counter-based prediction. But I'll ask the question, is this good enough? And you will hopefully tell me no, because we already did this exercise last time, right? How big is the branch problem? So I'm going to remind you the exercise we did with higher prediction accuracy numbers. So basically we have 20 pipeline stages. We're fetching 5 instructions per cycle. 1 out of 5 instructions is a branch, which means that there are 100 branches that we're fetching, and each 5 instruction block ends with a branch. How long does it take to fetch 500 instructions? If you have 100% accuracy, you're fetching 5 instructions per cycle. Basically everything finishes in 100 cycles because you don't mispredict anything. So your IPC is perfect, assuming there are no data dependencies, of course, right? Other stalls. Now, if you're 90% accurate, which may be possible with this 2-bit counter prediction, you get you get 10 of the branches incorrect. So for each one of those branches, you spend 20 cycles on the wrong path fetching, which means that you've increased your number of cycles to 300 cycles very quickly. So you fetch 200% extra instructions, and your IPC is quickly 1.6 bar, right? It sounds terrible. You've dropped from 5 to 1.6 immediately by just a 10% drop in accuracy. Okay, if you're unlucky, you're 85% accurate. Now your IPC is 1.25. If you're 80% accurate, which is still not bad accuracy, your IPC is only 1. So with 20% misprediction rate, you go from 5 IPC to 1 IPC. Essentially, you lost 400% performance, or 5x performance, depending on how you calculate it. And you also increase your energy rate. That's why it's not good enough. If you want to build a machine that's large, wide, and deep, and we know the reasons to build these machines because you have long latencies to tolerate, you cannot ignore the branch problem. Okay, so the key question is, can we do better? And people have actually invested a lot to do better over time. And these are very interesting mechanisms, as we will see. So last time and 2-bit counter predictors actually exploits a notion of predictability called last time predictability. They still look at the last few instances of the branch, right? People have found out that there's actually other types of correlations in programs that lead to better predictability of branches in programs. So one realization, very important realization, that was made in this paper, actually both realizations are actually made in this paper, is that a branch's outcome can be correlated with other branches' outcomes. I'll give you examples from real code, and you will empathize with it. This is called global branch correlation. And by tracking the directions of previous branches, the taken or not taken outcomes of other branches, not the branch that you're trying to predict, but other branches in the program, you can guess where this branch will go with much higher accuracy. And the second realization is that a branch's outcome can be correlated with past outcomes of the same branch other than the last time predictability. So if you look back, for example, I don't know, 16 iterations, maybe you'll find patterns that are more predictable compared to when you just look back one iteration or maybe 2 iterations for the same branch. This is called local branch correlation, and this is also employed in existing processors. So let's take a look at the first one. So if you've done your readings, this will be easy because the reading actually talks about both of them and combining them, in fact. So global branch correlation, this is the idea that recently executed branch outcomes in the execution path while the program is executing are correlated with the outcome of the next branch that you're trying to predict. So this is one example code. You don't need to know anything else about the code to guess that these 2 branches are correlated. Why? Because the first branch is testing condition 1 and branching based solely on that, and the second branch is testing condition 1 and condition 2 and branching based on that. Now, if you know the outcome of the first branch is taken, what can you guess? The next branch is also taken, right? Not true. You cannot guess anything if you know that outcome. But if you know the first branch is not taken, you know that the second branch is also not going to be taken, right? So there is some correlation. It's not perfect. You cannot guess the outcome of the second one perfectly because there's an and relationship over here. But if you know that this condition is false, which is implicitly indicated by the fact that you remember that this branch was not taken, then when you get to this branch, if you know this information, you can say, okay, this branch is also going to be not taken. Then the key question is, how do you actually know that information? And how do you actually supply that information? Basically, if the first branch is not taken, the second is also not taken. This is an example of correlation across different branches. That's why it's called global. It's global in the program. It doesn't need to be global so far away in the program, but it can be very closely executed branches. And we all write code like this. So another code example. It's a different kind of correlation. It's through the data dependency, but it's still a correlation, as you can see. Here, these 2 branches are not data dependent. They're actually independent of each other potentially, assuming this condition 2 is not set over here, which is the assumption. So if you look over here, this branch y sets, if condition 1 is true, the branch y is taken and a is set to 2. And this branch x later tests if a is equal to 0. Clearly, if this branch is taken, a will be set to 2, and this branch will not be taken, right? Okay, so the only thing that you somehow need to remember is where did the previous branches go, and using that information, you need to make an educated guess as to where should this branch go. Clearly, remembering all of this information is not feasible, right? And people have tried a lot to remember this information in programs, and there's a lot of creativity that went into it, but simple mechanisms that are not perfect work really well. And I'm going to give you an example of a simple mechanism that is not perfect. So, okay, another example. This can get even more complex, right? There's branch Y and branch C. They're testing 2 different conditions, and the first one is taken if condition 1 is true. The second one is taken if the condition 2 is true. And the third one tests both conditions, condition 1 and condition 2. So if Y and Z are both taken, then X is also taken. If Y or Z are not taken, then X is also not taken. So there's a very strong correlation relationship between these branches. Yes?
Couldn't you say that there is a flow dependency between these 2 branches? Is it basically like that?
Not necessarily. I mean, there's no data dependency between these branches because condition 1 and condition 2 are independent.
In the previous example where...
Yes, here, yes. Here there's a flow dependency for sure. Yeah, there's a control flow leads to some data, and then this data dependency is dependent on where this branch is executed. Okay, so before I give you the mechanism, I'll give you a real example. This was actually very interesting program. It was one of the spec workloads. Spec workloads were designed to actually test processors' performance, and people used to compete. They still compete with different workloads, but at that time, spec workloads were the big workloads where manufacturers, when they actually produced a processor, they would test their processor and figure out how fast their processors were. And this was one of the hardest branches. So this is an equation to truth table program that generates a truth table from a Boolean expression. And this was one of the hardest to predict branches over here, the second one. It's very similar to, if you look over here, something like this. So if B1 is not taken and B2 is not taken, then B3 is certainly taken in this case. Basically, this branch is correlated with these outcomes. And it turned out all of the branch predictors were failing. You would be getting 70 to 80% accuracy in this workload. But after the invention of the global branch predictors that take into account this correlation across different branches, this program became not so interesting anymore. Basically, the prediction accuracy became 95% or so, maybe. It's still interesting, but not so interesting. And the machines that implemented global branch predictors basically did extremely well in this program. So how do you capture global branch correlation? So this is a real example. There are many, many other real examples. So idea is very simple, actually. We want to associate branch outcomes with global taken, not taken history of all branches. So we're going to keep a history of taken, not taken behavior of some number of branches. I say all, but all meaning that there are different branches that contribute to this history. And we want to make a prediction based on the outcome of the branch the last time the same global history was encountered. So let's assume that you see the last 4 branches that you executed were all taken. And you're going to remember what you did last time when you saw that history, when you executed this branch. So all were taken. Last time you did not taken. And if you see that history again, taken, 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 you're going to do not taken again. So you can think of this as a pattern, learning patterns in a sense. If the history was not taken, not taken, 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 and the last time the branch was executed, it was taken, then you'll learn to associate the history, not taken, not taken, taken, taken history, with a not taken outcome. Basically, we're going to remember what happened the last time we saw that pattern history for the branch. So to be able to do that, you need to keep track of this global taken, not taken history for all branches in a global history register. I'm going to show you an example of this with a picture. This is an n-bit register that encodes the outcomes of the last n branches. And we're going to use that to index into a table that recorded the outcome that was seen for that value, global history register value in the recent past. This is called the pattern history table. And we're going to still use 2-bit counters in this case. Again, you can use 1-bit counter, 2-bit counters, 3-bit counters. It's going to be very similar to the state machine that we discussed. That's a design choice. So this is called the global history or global branch predictor. Why is it 2-level? Because it uses 2 levels of history. You don't just look at the outcome of this branch last time. You look at the history in the global history register. Where did the past n branches go? And what was the outcome that I had for this branch based on that particular history the last time I saw it? Not necessarily the last time I saw it, but with some hysteresis, depending on how many bits of counters you have. And this is the example, basically. This is the implementation. You have 2 levels. First level is this global branch history register with n bits. N could be 16, N could be 256. 256 is too much. Many existing systems have 16, for example. They look at the last 16 taken, not taken outcomes. This is the direction of last n branches. And basically, of course, it depends on how you encode this, but the last bit can indicate the immediately previous branch's direction, and the first bit over here may indicate the branch that was executed 16 branches ago, right? So this is the global history register. So we're going to keep updating this history while the machine is running. If a branch is predicted taken, we're going to shift in a 1 to this, and then shift out the oldest prediction, or oldest outcome. If the branch is predicted to be not taken, we're going to shift in a 0 over here, and shift out the oldest one. So you keep updating this history. It encodes the directions of the last n branches, okay? The second level, you have a table of saturating counters for each history entry, potential history entry, and this basically tells you the direction the branch took the last time the same history was seen. So we're going to index this pattern history table with the value that you have in the global history register. So if you saw this history last time, where did the branch go? If this was 1 bit, it will say the branch was taken. or the branch was not taken. And if you see the history, it's exact same history again, you're going to index into that same location, and you're going to get that bit saying taken or not taken, and you're going to do whatever that outcome that was recorded over there was. Does that make sense? Basically, you're remembering what you did the last time you saw the history, and you're predicting the branch based on that remembrance, that memory. And all of these values that are over here encode different histories. This is the case where all of the bits in the history register are 0. This is the case where all of the bits in the history register are 1, which means that if you have n bits in your history register, you have 2 to the n entries in the pattern history table, clearly, right? And if you see the same history again, you're going to do whatever you did the last time, subject to however you update these bits over here in the state machine. If you have a last time predictor over here, this will be a single bit. If you have a 2-bit counter predictor, it'll look like this. If you have 3-bit counter, you can imagine adding more stuff over there. Okay? Okay, now that you know the concept, it's very clear. Let's take a look at a code example over here. The paper that I assigned to you actually does a very good job of explaining this. I'm going to go through this relatively quickly. Basically, this is a very simple loop. The first loop iterates 100 times. The inner loop iterates 3 times, as you can see. This is kind of the test that you do. The inner loop iterates from 1 to 3, and the outer loop is usually taken. Let's start with the outer loop, the branch that is testing the outer loop over here. If you actually do all of the calculations, this branch clearly tests I. And last 4 branches, previous 4 branches test J. Actually, it should be last 3 branches over here. Last 3 branches actually test J over here. We're going to fix that. So the history, whenever you come to this I, is always like this. Taken, 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 not taken. Because they're all, the last 3 incarnations of J are like that, basically. The loop executes 3 times. And if you get to the state, whenever you see this history, you should predict taken, because that history is essentially the prediction for that branch. So you predict taken for I. Whenever you see this history, you associate the outcome as taken. Now, if you next history will be taken, taken, not taken, taken, because this is going to be taken in this case. It's usually taken, as you can see. Only 1 out of 100 times it's mispredicted. So you shift in the last outcome. So the next time you go, next time you execute a branch, you will use the next history over here, taken, taken, not taken, taken. And the branch is always taken in this case. If you look over here, this branch, the first time you enter the inner loop, it's always taken because it's a static bound for the loop index. So you know that this history will always lead to a taken outcome. And whenever you update it once, the next time you see it, it's going to be taken. The next time you see it, it's going to be taken. So you're going to always predict this correctly. That's true for the next iteration also. That's true for the third iteration also until you get over here. Anyway, I went through this relatively quickly, but if you're done your reading, it should be very clear. And I would definitely recommend that you do your reading. It's very simple. It basically shows how the global history register, they call it Gshare in the paper, changes based on the outcomes of the branches that you execute and what are the predictions that you do in each global history register state. So for all of these 3 global history register states, you're always correct once you warm up the predictor, meaning once the predictor figures out what you should do in that state. Only in this case, you're usually correct because you're getting out of this loop and you'll do something else after that. Okay, so this predictor, as I said, was implemented in pretty much all machines. Actually, all machines have much more sophisticated predictors right now, but Intel Pentium Pro was the first widely commercially successful out-of-order execution engine that was built in 1994 to 1996. And it had this 2-level global branch predictor. Basically, they realized that branches are a huge problem for them, so they included this one. So they had a very small global history register, only 4-bit global history register. And they had multiple pattern history tables of 2-bit counters. Basically, which pattern history table to use was determined by lower order bits of the branch address. I'm not going to go through this in detail. You can read about this. It's well documented in history right now. But you can see that you have a very small global history register, and you can actually improve the prediction accuracy significantly. Okay, any questions? How many of you have done the reading? Okay, good. We need more people. So people have actually improved global history register accuracy. You may say that, okay, this global history register, it's a hack. I mean, there's some intuition behind it clearly, based on the programs, right? The programs clearly show this correlational behavior. But can you do better? It turns out adding more context information enable you to do better. Because whenever you look at this global history, different branches may see the same global history, but they may actually lead to different outcomes in the execution, because we're using a single global history for all branches in this case. If you add more context information to the global branch predictor, you can actually improve accuracy. And if you've done the reading, you've seen the Gshare predictor. It's called Gshare. It's essentially a global history register that's hashed with the branch program counter. So you add more context information. This is the idea. You don't just use the branch history register to index into the pattern history table to get a prediction. You basically form a hash, add more information before you decide which pattern history table entry to use. Basically, when you see this branch history register with this branch address, then you figure out what you've done the last time you've seen this combination, and then you do the same thing this time you execute this context. Does that make sense? You don't just rely on the branch history register to make your prediction for the branch, but you rely on the branch address as well in this case. So this is one example of adding more context information to use for prediction. This also helps, it also enables better utilization of this array, because whenever you're adding more information to index into some structure, you're also randomizing the indices. As a result, you get a better utilization of this pattern history table, of the 2-bit counters. Of course, the downside is it increased latency, because now you have an XOR gate, or bitwise XOR, before you index into this pattern history table. I just want to give this because this is one example of adding more context into your, here. You can add even more context. I mean, you can use other values that you have in the program, for example, to index your branch predictor to get better prediction accuracy. But of course, then it becomes more complicated. What do you actually add becomes difficult, and I'll leave it there. This is an example place where maybe more machine learning techniques can be more useful going into the future. Okay, let me review where we are. This is the one-level branch predictor that we've seen. You basically use the program counter to make a prediction in terms of direction. And we've seen that last time. Predictor is an example of this. 2-level global history branch predictor doesn't use the program counter. It uses the program counter to get the target address, of course. But it does use the global branch history register to make a prediction. But it only uses the global branch history register to make a prediction. This is the first level, which direction earlier branches went, and which direction this branch went when you saw this history last time. The Gshare predictor uses both information, not just the global history register, but also the program counter to index into this direction predictor to make a prediction. And as a result, it's more accurate. And if you read the reading that I assigned, you see the accuracy of it also. In fact, that's the reading that I assigned to you was the first work that proposed this Gshare prediction. Okay, any questions? I'm done with the global branch predictors. Now let's look at the local ones a little bit, in a bit more detail before the break. People have also figured out that a branch's outcome can be correlated with past outcomes of the same branch if you look back in the history. This is local branch correlation. And your reading, again, has a very nice example of this. This is an example where you have a loop, and I'm going to read this over here. If the loop test, you have a loop test that's done at the end of the body, the corresponding branch that loops will execute the pattern 1, 1, 1, 0 to the n, where 1 and 0 represent taken and not taken respectively. Basically, you execute this loop 4 times, as you can see, or 3 times, actually, in this case. And n is the number of times a loop is executed, right? Clearly, if we knew the direction of this branch, actually, I think you executed the first time, 1, 2, 3, 4. Yes, you executed 4 times. And the 4th time, the last iteration, you predicted the branch is not taken. The first 3 times the branch is taken, clearly. Clearly, if we knew the direction this branch had gone on the previous 3 executions, then we could always be able to predict the next branch direction. Right? That's true, because it always repeats the same pattern. 1, 1, 1, 0. Taken, 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 not taken. Taken, 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 not taken. Taken, 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 not taken. So how do you actually do this? Basically, this is one example. This is different from what I've shown you over there. But basically, to predict a loop branch perfectly, you want to identify the last iteration of the loop, when it switches from taken to not taken, right? So if you have a separate pattern history table entry for each local history, so if you keep the local history of this branch, And if you have a separate history table entry, separate counter, or separate single bit, now you can distinguish different iterations of a loop, because you'll have a different history every time you execute a single iteration. And these different histories will map to different locations, and the one that will give you the not taken outcome will be this one, in this case. This is one example, basically. All of the other ones will give you a taken outcome, meaning that you're still iterating in the loop, but one of them will distinguish that the fact that, okay, this is time to exit the loop, and this history indicates the fact that the branch should exit the loop. And then you predict the branch is not taken. Clearly, this works for short loops, meaning that your history needs to be the pattern that you have for the branch, let's say 1110, that's a 4-bit pattern, needs to be encapsulated by your history register length. So if your history register length is 16, 32, that's great. You can identify predictable loops that terminate within 32 iterations. But if your loop iterates for, let's say, 257 times, you need a history of 257 times, and you cannot identify that. So that's a downside. So let me finish this, and then we'll take a break. So basically, the idea is very simple. Again, in this case, we have a history register, but we have a per branch history register. We don't let other branches update this history register. Only for this branch, we update the history register. We record where this branch went the last n times it was executed. And you make a prediction based on the outcome of the branch. Last time, the same local branch history was encountered. It's also called the local history or local branch predictor. Again, it uses 2 levels of history. The first level is per branch history register, and the second level is the history at that history register value. If you see this branch again, and if you have the same history, what did you do last time? If you exited the loop, that's great, exit the loop again. And it looks like this, basically. Very similar, except instead of having a single global history register for all branches, this is local history registers that you have on a per branch basis. Each of them is for one single branch. And the second level is a table of saturating counters for each history entry, and you should have it for every single branch also separately, but I'm not going to go into that in detail over here. So basically, it looks like this. You use the program counter to get a history, and use that history to index into a 2-bit counters, and that tells you taken or not taken. So the key thing to remember is this keeps track of which direction earlier instances of this branch at program counter X went. Okay, so maybe we should take the break at this time, unless there's a burning question in local history. Okay, you can save the questions over the break, and I'll see you soon. Let's pick up where we left off. Remember, we were discussing local history predictor. Now we have a good idea of how local history prediction works. We've seen a bunch of different prediction mechanisms, actually. Static mechanisms, and then last time prediction, dynamic mechanism, and then 2-level mechanisms, global history register-based mechanism, and then local history register-based mechanism. The question is always, can we do even better? It turns out prediction accuracy goes up to 90% or so on many programs after you use this 2-level history registers. But people have figured out that you can do even better because predictability of branches actually varies. Some branches are more predictable using local history because they may be loop branches that can fit into this history. Some branches are more predictable using global history because they may be these branches that are very much correlated with other branches that are executing in the program. For other branches, a single bit is enough. For example, if you have a loop branch that's iterating 1,000,000 times, probably you don't want to use any of these sophisticating mechanisms because you're going to mispredict only once out of 1,000,000 times. Maybe that's okay, right? Once out of 1,000,000 times. Once out of 100 times may not be okay, but once out of 1,000,000 may be okay, if you cannot figure that out easily, of course. If it takes a lot of hardware to figure that out, maybe it's okay to mispredict that once out of 1,000,000. So for those branches, a single bit is enough, perhaps. And for some other branches, a simple 2-bit counter is enough. And for some other branches, just a prediction supplied by the program is enough, right, with a static mechanism. So there's a lot of heterogeneity in the predictability behavior of the branches. And people have realized that, as a result, existing branch predictors are very, very heterogeneous because there's no one-size-fits-all branch prediction algorithm for all branches. And the idea is very simple. That's actually proposed by the reading assignment that you have. you exploit this heterogeneity by designing heterogeneous or hybrid branch predictors. It's a very simple idea. What is the idea? Use more than one type of predictor, or use multiple algorithms. If you think of all of these different predictors, they're actually employing different kinds of algorithms, hardware algorithms. They're hardware optimized algorithms, but they're algorithms to actually predict branches. And use more than one of these algorithms and select the best prediction for some definition of the best, or for some prediction of the best. Now you need to predict which one is the best. There's another prediction mechanism that you need to employ for this, right? So for example, you may have a hybrid predictor of 2-bit counters and a global predictor. This is a hybrid of 2 predictors. You may have a hybrid of global predictor, local predictor, 2-bit counters, and a single-bit counter, right? That's 4 predictors. And existing machines are not that different from that. In fact, existing machines try to identify these branches that are really easy to predict and predict them with simple mechanisms, like a simple single-bit counter. Single-bit counter is last time prediction, right? They basically use the more sophisticated algorithms for branches that are more difficult to predict. Yes? Yeah, we're going to talk about that. We're not going to go into a lot of detail, but you need to build another predictor or selector for that. Let's talk about the advantage of this first before we go into which one's the best. So it turns out this leads to better accuracy because different predictors are better for different branches. Different predictors may be better for the same branch at different times of execution also, because branches also change behavior dynamically depending on the data patterns, for example, that the branch is looking at. So overall, you get better accuracy with this. And also there's another benefit to doing this, which we didn't really fully talk about, but there is a problem with warm-up, in the sense that whenever you start a program, this predictor starts getting trained. And if your predictor uses a lot of information, let's say a 32-bit history register, it takes a long time to train that predictor, basically populate those 2-bit counters. You need to see basically all of the interesting histories to be able to make an intelligent decision the next time you see the same history, right? And there may be a lot of histories that the branch goes through. So it takes a long time to train these 2-bit counters to get to a state where you're comfortable doing predictions. This is called warm-up time. But some other predictors are very fast to warm up. You see the branch once. Last time predictor just needs to see the branch once, right? And after that, it's going to predict based on what it's seen. So some predictors are easy to warm up, some predictors are hard to warm up. If you have many different predictors, you can pick the predictor that's warmed up at that point that seems to be accurate. How do you do that? You need to use heuristics. And existing systems actually do all of this. So this advantage, clearly you need more hardware. I didn't write that over there, but clearly you need more hardware to be able to do that. But you also need a meta predictor, as your colleague mentioned, was curious about, or a selector to decide which predictor to use. Now, to be able to decide which predictor to use, you need to make another prediction, right? That's why people think this is actually a very fascinating topic, and it's not easy to actually design these predictors. Of course, this also leads to longer access latency. So the paper that your reading assignment actually covers one example of this. I'm going to give you another example. This was designed in Alpha 21264, which was the fastest machine of its time. It doesn't exist anymore for various reasons, but not because of technical reasons, I should say. Basically, these folks who designed this machine also figured out that minimum branch penalty is 7 cycles. 7 is not that long by today's standards. And they typically saw that the branch penalty is more than 11 cycles. And they basically designed this sort of predictor. So as you can see, this is a local predictor and a global predictor. Very similar to what we've seen. This is a global history register of length 12. And you have 2 to the 12 2-bit counters corresponding to the pattern that you see every time you encounter that history over here. And then you have a local predictor that's indexed with the program counter. You get the local history for that program counter, and that's 10 bits. And then you index that into a pattern history table that has 3 bits per entry, as you can see over here. So you get a local prediction from your local predictor, and you get a global prediction. Now you need a selection mechanism, which is what this is. So your final prediction is decided by your choice predictor. And here they don't give a lot of information, but they use part of the global history to decide which one actually does better. So for example, you can say, every time I see this global history, this predictor is doing better, so I'm going to choose that. And again, they use 2-bit counters over here to add hysteresis to that decision. So its principles are similar, but you could of course use other information also. You could of course, you could use more information. These folks found out that this choice predictor is good enough for their purposes and for their area budget. So they basically have a large state associated with branch predictor. You can see that, well, they don't say this branch predictor state, but it's actually quite large. But they also have a large BTB, 48K target addresses, and they store it in the instruction cache in this case. And what they do is, whenever you context switch, whenever you switch from one program to another program, they reset all of the predictor tables so that they don't use information trained by a previous program. This may or may not be good, but they found out that it's, the information that you gather from program A doesn't carry over for better predictions for program B. Other people have proposed saving the state of these tables into some memory location, and the next time you load the program, you load the state of the tables also, but that's too much overhead in terms of loading these tables. And also there's another issue. If you actually save these tables to a memory location, these become more architectural, right? Right now, these are purely microarchitectural. Nobody needs to know about this. The operating system doesn't know about this. The programmer doesn't know about this. Every prediction is done microarchitecturally. No software knows about this. But if you need to save these tables, then you need to create some sort of structure to be able to save these tables, and they become more architectural. And if you're interested, this is the paper that I had recommended in the past. It's a bit harder to read, but this is from that paper directly. And many existing systems actually use this sort of predictor. It's even more sophisticated. They have other predictors, they have loop predictors, they have indirect branch predictors, as I will briefly discuss. So are we done with branch prediction? Hybrid branch predictors actually work well. For example, they see 90 to 97% prediction accuracy on average, but some difficult workloads still suffer. For example, a compiler that many of you may use, GCC, the maximum IPC with tournament prediction with the previous predictor is 9, assuming you have all of the other bottlenecks sorted out somehow, you don't have data dependencies. But if you actually could perfectly predict branches, you could go up to 36. This is assuming a machine model that actually can execute many, many instructions per cycle. You don't have bottlenecks. But branch prediction actually bottlenecks your instructions per cycle performance. So I could do the same thing and go through, okay, what happens if you have a machine, 97% prediction accuracy, and how much instructions are wasted? I'm not going to do that. Now you know the importance of the problem. And the goal is to make it much more efficient and much higher performance. As a result, people have been working on many other predictors. I'm going to give you a couple of examples over here. So loops we've been discussing, and several of you had the idea that, okay, maybe we could actually do the loops better, and certainly the designers of the machines also had the idea that maybe we could do the loops better. So existing machines employ loop branch detectors and predictors. They basically try to detect loop branches, and loop branches are easy to detect. If you have a backward branch and you keep executing the branch many times, you can detect it. And if the branch has a consistent iteration count, every time you enter and exit the loop, you could predict that. So, for example, if you enter the loop, you see this loop branch, and that loop branch is executed 125 times, you record it somewhere. The next time you see that branch entering the loop, you basically predict it's going to be executed 125 times, assuming that's true. If that's true, then you'll never mispredict that loop branch again. Okay, I think I already said this basically. And this is first used in Intel Pentium M, which was the beginning of the current generation of the Intel's highest performance processors. Perceptron we're going to talk about. This is an example of learning correlations of branches between individual branches, correlation of directions between individual branches. And this assigns weights to correlations using the simplest possible model of a biological neuron. So Perceptron is a biological neuron that is trying to mimic human neurons. And I'm going to give you an example of this before we go into it. But essentially, this is also used, and this also performs very well. And it's used in some AMD machines as well as some Samsung machines. And people have also developed these history lengths. So people figured out that history length is a big effector of prediction accuracy. Some branches, like small history lengths, they can be predicted accurately. Some branches require very long history lengths. Not loop branches. Loop branches we can potentially handle over here, or maybe you don't care if it requires a million iterations, right? But some branches that are dependent on data patterns and different kinds of patterns in the program, different kind of correlations, may be dependent. For example, the branch you're executing right now may be dependent, maybe correlated with a branch that was executed 10,000 branches ago. It's possible. These programs have different data dependencies, right? This branch, 10,000 branches ago, may be testing a condition. This branch is also testing. Now, if you had a branch history that was 10,000 length, maybe you could capture this correlation. But of course, a branch history register of length 10,000 is a bad idea. The way at least I described it, right? Because you need to have 2 to the 10,000 entry 2-bit counters in that particular design. So people have designed different ways of taking into account different history lengths by using small prediction structures. I'm not going to go into the details of this, but this paper by Andres Seznek talks about this geometric history length branch predictor that has many different tables. And some of the tables are associated with small history lengths, some of the tables are associated with very large history lengths. And there are sophisticated algorithms to decide which tables should you use and which tables, how you should update the tables. Let's go through these in a little bit more detail. I'm not going to go through this. I already said this actually. If you look over here, this is a nice paper that you can read if you're really interested in it. But basically, this is the mechanism that I described. Whenever you see a loop branch, you figure out the first time you go through the entire iterations, what is the limit, how many times you execute this loop branch. And the next time you see the loop branch, you basically start counting. And when you reach the limit, you say the branch is going to be predicted, not taken. If you don't reach the limit, you basically predict the branch to be taken, assuming the branch executes the loop the same number of iterations every time, which is a big assumption. That may not be true. If that's not true, loop branches also become difficult to predict. But there may be patterns in loop branches. This time you execute 3 times, next time you execute 8 times, next time you execute 9 times, and you repeat this 3, 8, 9, right? But you cannot do it easily with this one. Okay, this also has an indirect branch predictor logic, which we may talk about once we get to that. So let's talk about Perceptron. So Perceptron is very interesting, and this is one of the, actually maybe the only successful example of the use of machine learning in commercial hardware design in hardware so far. But there are a lot of other opportunities also. So what's the Perceptron? Perceptron was introduced by Rosenblatt in this book, if you're interested in reading it. It's a simplified model of a biological neuron. People were fascinated with how neurons work, and they tried to mimic those neurons with hardware in the past. It's also a simple binary classifier, meaning it essentially maps an input vector x may be some observations that you make, to a 0 or 1, right? You get this vector x, you say it's true or not true, right? You could detect a language, for example. You hear some words, which is an input vector x, and the neuron fires, says it's German or not German, right? Or some other language. That's a simplistic way of thinking about how the brain works. Okay, so input to the neuron, Perceptron, is vector x, and it learns a linear function, if one exists, of how each element of the vector affects the output. So you store this in an internal weight vector. So internally, you have a weight vector. So this is actually the simplest example of a neural network. It's a single layer neural network. So right now, neural networks are very popular, but they have many, many layers. But this is a very simple single layer neural network. So you basically learn these weights that are associated with different input vector elements. So, and the prediction that you make in terms of output, how you map this input vector x to a 1 or 0 is, you basically do a dot product of the weight vector and the input vector, and then you add a bias to it. Bias enables you to be able to say, okay, I don't really need to, there's a bias associated with what I learned. And then if it's greater than 0, and you check whether it's greater than 0. Let's take a look at it in the branch prediction context. So in this case, for example, you can, your input vector x in language detection may be the words that you hear, and weights are the weights that are associated with each word that you've learned in the past, whether it's German or not. And if you hear a bunch of words with an input vector x, let's say 100 words, each of them has a weight that you learned in the past. This word is very likely German, this word is not very likely German, this word is very likely German. And you do this multiplication for all of the words that you've heard with the weights that you've learned in the past. And then you add a bias, maybe overall bias, saying that, okay, this sounds like German. And then if it's greater than 0, then you say, okay, I think I'm hearing German. If it's less than 0, you say, okay, I don't think this is German. And basically the fact that how close to 0 you get may be an indicator of how close to German that language might be. You may actually use that information also. So that's the idea. That's a very simple idea in language detection, for example. In the branch prediction context, it's very similar. We don't use words. We use branch history register bits. So you basically have these vector, and this tells you which direction these different branches went. The last m branches that you executed went. And output is the prediction for the current branch. Now, what you need to learn is the weights associated with each of these prediction bits. What is the weight of the prediction bit, the global history register bit, in terms of its effect on the output? If this bit is taken, should I predict it as taken? If you have a high weight, that says, okay, you should really, high positive weight, that means that you're very much correlated with that particular bit. I'll give you an example right now. Basically, a perceptron looks like this. This is the input vector x. This is the bias weight. And you basically multiply each input vector element with the weight that you learned and sum them up, including the bias, which is the function over here. And if y is greater than 0, you make a prediction. If y is less than or equal to 0, you make some other prediction. And the idea is to use this perceptron to learn the correlations between branch history register bits and branch outcome. So a perceptron learns the target Boolean function of n inputs over here and the bias over here. So let's take a look at it from the context of branch prediction. Each branch is associated with a perceptron, so think of this as dedicated to a single branch. So you contain a set of weights. Each weight corresponds to a bit in the global history register and tells you how much that bit is correlated with the direction of the branch. If this has a positive correlation, so for example, if this branch that you're predicting is taken and this bit is also taken and it also has a very positive correlation, then this means that you have a large positive weight. Or another way of thinking about this, if this bit is very highly correlated with the outcome of the branch, positively correlated, this weight will be very positive. So you can think of this as if this bit is taken, you're going to predict the branch as taken. And how do you figure that out? This weight is very large. You could also have a negative correlation, meaning that if this bit is negatively correlated with the potential outcome of the branch, whenever this is not taken, you should predict taken, or whenever this is taken, you should predict not taken. For this branch, you get a large negative weight. Make sense? So you basically have this large positive and large negative weights, and you learn these weights through some function, which I'm not going to go through in detail, but you can read the paper. Now you can make a prediction. You can express the global history register bits as 1 or -1, taken or not taken, depending on how you do the encoding. And whenever you're trying to predict a branch, you take the dot product of those global history register bits, expressed as 1 and -1, and take a dot product with the weights. So if this is 1, you multiply it with this weight. If this is -1, you multiply it with this weight, and then you add them up. And if the output is greater than 0, you predict as taken in this particular case. Very much similar to the German example that I gave you, right? You learn for each word a weight that indicates your confidence as to whether that word is in German, and you get a large positive weight if that word is German. And if the word that you hear is not German, then you get a very large negative weight. Similar, in this case, if this is going to be taken, then you get a very large positive weight. If this is taken and this is going to be taken, you get a large positive weight. Otherwise, you get a large negative weight. Make sense? Okay. So if you've done neural networks or machine learning, this will be simple because it's the simplest form of neural network. So the prediction function is very simple. You get a bias weight also, you get a bias of the branch that's independent of the history. I'm not going to go through how it's learned, but you can see the training function also. Every machine learning the method is really statistical, and you have a statistical method of training here also, as you can see, and the paper discussed that. Based on the outcome that you see of the branch, and based on the bits that you see in the global history register, you change the weights. So if the outcome was taken, and if one of the weights was not taken, then you change the weights accordingly, right? You basically increase the negative correlation that you see in that case, right? If the outcome is taken and if one of the bits is taken, you increase the positive correlation. So you need to have a training function, and training functions are a very hot area of research in machine learning algorithms, clearly. So there's no perfect training function. You just need to increase the accuracy for the application you have at hand. Yes?
Learning
Yeah, absolutely. All of this is in hardware, basically. This is all built into hardware. I'm not going to telling you exactly how it's built into hardware. There are a lot of challenges. Even this very simple prediction mechanism, there's a challenge, right? Because you need to implement this function very quickly, right? So in this case, this is a single layer network, so backpropagation is limited to this algorithm. Yeah. But if you actually do more sophisticated learning, yes, you need to implement it in hardware also. Maybe for branch prediction is too long latency, potentially, but people actually design hardware to actually do that backpropagation today. Very sophisticated hardware. Google's TPU is one example. Recently, Tesla announced their own chip to actually do inference for learning, and they do all of that in hardware also. But maybe for branch prediction, it's very, branch prediction may not be a good application for that because the latency requirements are very low, right? Okay, it's fascinating, right? Okay, so I've already given you this basically. This is the dot product of global history register bits and the perceptron weights, and you basically take that dot product, you add the bias bit, and you get a y. You compare y to 0. That's the prediction function. And you need to do this in one cycle, right? And that's the challenge. You need to do a dot product computation, an addition, and a comparison to 0 in one cycle. How do you do that? It's very intense. Even a simple network like this takes a long time if you want to do it in one cycle. So people actually built mechanisms to pipeline this, do it early on, much before you see the branch, you try to get the predictions actually in shape. How do you do that? I'm not going to go into detail. Okay, so let's talk about the advantages and disadvantages. Clearly, this is a more sophisticated learning mechanism. It gets you better accuracy. In fact, I've implemented this when I was a PhD student doing my PhD thesis. I need a better branch predictor for the stuff that I wanted to do because I wanted to tolerate memory latencies better by doing prefetching in a nice way, executing the program just for prefetching. And if you want to execute the program for prefetching, you need to have a good branch predictor to find those cases, to find those things to prefetch. And this actually buys you better performance. I implemented this, and this is one of the ideas that actually works off the bat. It reduces the misprediction rate significantly very quickly. But of course, it comes out with a hardware cost. It's hard to implement, so you need an adder tree to compute the perceptron output. And you're at a very tight part of the machine. You need to do this prediction very quickly. And there's a downside of perceptron that other people have fixed with adding more information. This can only learn linearly separable functions. I'm not going to go through this in detail, but all machine learning algorithms have some downsides. They're as good as the data that you feed them, first of all, but the second is that they may be able to learn or not learn some particular type of functions. In the case of perceptron, it's very simple. It cannot learn XOR type of correlation between two branch history bits and branch outcome, basically. Basically, if these two branch history bits are related, you take the XOR of these bits, and the outcome is really an XOR function of those bits. You cannot learn this, because there's no way it will be able to adjust the weights so that you can get the XOR function. It's sad for perceptron, but the same folks who developed this algorithm later developed mechanisms to overcome this by adding more information into the system. So usually you can add more information to the system and learn better, overcome some of these learning deficiencies, I should say. Okay, so this is a successful example of use of machine learning in processor design today. Is this the state of the art? It turns out this doesn't do as well as what humans can do. Well, maybe some smart humans can do. So people have observed that using multiple history lengths, this is the state of the art actually, with some sophisticated mechanism. I'm going to give you the state of the art in a little bit. Basically, as I said earlier, different branches require different history lengths for better prediction accuracy. And people have found out that having multiple pattern history tables or 2-bit counters indexed with global history register with different history lengths and intelligently allocating entries to different branches can buy you better performance or better accuracy. It looks like this. This is a simplified version. So for example, this is an example where you have a base predictor. You don't use history here. You just use the program counter. Another predictor uses a short history. And there's a lot of hashing that goes on. And you don't just have an index of 2-bit counters, but you actually allocate these 2-bit counters to these different histories. And then the next predictor has another longer history. Next predictor has another longer history, and this predictor has the longest history. And these folks found out that using geometric history lengths is actually good. So this can actually have history lengths of 1,000 or maybe 10,000, depending on how you design it. And you don't need a 2 to the 10,000 entry predictor to be able to do that. Okay. So if you're interested, you can read this paper. So let me give you the state of the art real quickly. It's state of the art circa 2016, but many mechanisms are similar. Still, some people, you can still incorporate Perceptron into these, I think. But this is one example. Again, I'm not going to go into the detail of this. There's a lot of statistics applied to this. So this is the TAGE predictor. TAGE means this tag geometric history length predictor that kind of looks like this. You have these many, many tables. Some of them have very long histories, some of them have very short histories, so that you identify different branches. And you take the output of that. And that's not enough. On top of this, there's some global, local, and whatever it's called. You don't need to know about skeleton, but different types of histories that people build. And you input that into a statistical correlation engine that basically guesses whether this is good or this is good. And then selects one of those. Either picks this one or this one. But that's not enough because there are some other branches that are loops that are much better predictable with the mechanisms that we've discussed. So you need to treat the loops separately. So essentially, it's a very sophisticated mechanism, as you can see. And this is an area of research still. And I believe machine learning methods still have good potential, even though they may not be the best methods today. Okay, so there's something that I should discuss over here. There's something called confidence over here. As humans, whenever we make some prediction, we also implicitly or explicitly assign confidence to our predictions, right? People have found out that that's a good idea for machines also. Basically, that's the idea of estimating if the prediction is likely to be correct. Right? You make a prediction, you say, but I'm maybe 55% confident in it. You make a prediction, but I'm really 99% confident in it, right? If you can make this, then this could be useful for many things, right? Basically, it could be very useful in deciding how you should speculate in the machine. So for example, if you think that you're only 0% confident in the prediction, maybe you should invert the prediction, right? If you predict a taken, change it to not taken. That's essentially a better prediction mechanism. It's not very easy to do. Or you could say, okay, I fetched this branch, I'm really not confident in this prediction, maybe 50%, I'm going to save energy. I'm running out of battery, right? So stop fetching at this point until I resolve this branch. That may be a much more intelligent way of handling the branch than just fetching a lot of instructions that you're going to flush anyway, right? Or you could maybe switch to some other way of handling branch, which we may talk about if we have time. For example, you can say, okay, I'm not very confident. There are two paths after this branch. I'm at a fork, and I have the mechanism to fetch from both paths. And I'm going to use that at this point in time. If you have the hardware to be able to do that, then this may be a good way of handling that branch, right? Or you could switch to some other thread at that point. If you have the ability to do that, that might be a good idea, right? Even though you're optimizing for this thread's performance, you say, I'm at a point I'm really not confident, so maybe I should really switch to some other thread at this point, right? So there could be many, many uses of this confidence estimation. It was proposed over here, and if we get to it, we may actually see it. So it's very similar to how humans behave, in my opinion. Okay. It's fascinating, right? I think so too. Yes?
On the previous slide, you had whether to keep fetching on this path.
Mm-hmm.
So the branch predictor has chosen this path.
Yes.
But if it doesn't keep fetching, will it just idle?
Stall, basically. Yeah, at that point, you stall until the branch is resolved. When the branch is resolved, you know the outcome anyway, and then you fetch from the correct path.
Okay, but wouldn't that only conserve energy?
Exactly.
It wouldn't make it faster.
Yeah, it won't make it faster, but if you're not confident, maybe that's what you should do, right? Depending on the environment you're in. You look at other factors. If you're running out of battery, maybe it's not a good idea to push for performance at that point in time, right? So this enables basically many, many other decision-making processes. That's why it's interesting. Okay, so let's talk about some other ways of handling branches until the end of the lecture. So we've seen a very good idea. Branch prediction is a great idea, actually, and people have been exploring it, and there are many papers written on it, and I believe it's one of the hardest problems in the design of computer architecture today. It's probably even harder than the memory problem, actually. Memory is hard. It's the major bottleneck today, but if you really want to get a little bit better prediction accuracy in branch prediction, it's even harder, today at least, which means that there needs to be a lot of creative ideas. But let's take a look at an idea that is, I should call it a terrible idea. It's good for you to see these ideas so that you can actually, in the future, evaluate ideas in an intuitive way. And it's called the idea of delayed branching. It's also called a branch delay slot. Actually, the MIPS architecture that you're implementing has this for the branches as well as the loads. So they have a double terrible idea in their ISA design. But let's take a look at why it's a terrible idea, at least within this context. It may sound like a good idea, but if you actually are thinking about the future, it turns out to be a terrible idea. Okay, so the idea is very simple. I actually gave you this idea before. The semantics of a branch instruction today is after you execute the branch, the next instruction you execute is either the target or the fall-through instruction. There's no delay, right? You basically immediately execute the branch. You either go to the target or the next instruction. So some people thought it was a good idea to change the semantics of a branch instruction such that the branch takes effect after n instructions or after n cycles. Let's take a look at n instructions in the case. Basically, you delay the execution of a branch or delay the outcome of the branch taking effect. So n instructions or delay slots that come right after the branch are always executed regardless of the branch direction. So you get to the branch, you execute it, you figure out you need to go somewhere, but the n instructions that come after the branch in the code are always executed. Why? This gives you some time to determine the direction of the branch, right? If you have a pipeline machine, and if the branch doesn't take effect until some number of instructions, you can fetch those instructions into the machine safely and execute them, and don't think about these instructions are going to be flashed or not, because they're not going to be flashed. Because the branch will not be affecting them. Branch will be taking effect after n instructions. That's the idea. And the idea was developed exactly for this purpose, thinking about pipeline machines. If you're pipelining, and if you need to figure out what instruction to fetch next, and if the branch resolves after n cycles, why not write your program such that n instructions after the branch are always executed? And it's the programmer's job to figure out what to put in those n delay slots, or the compiler's job. That's the idea. So the key question is, how do you find instructions to fill the delay slots in this case? So a branch must be independent of the delay slot instruction. I'm going to give you an example of this. A branch must be independent of the delay slot instructions. So if you have an unconditional branch, it's not a problem. It's easier to find instructions to fill the delay slot. But if you have a conditional branch, now the condition computation should not depend on instructions in delay slots. And it turns out it's very difficult to fill the delay slot. And this is not the hardest problem with this approach. This is one of the problems. The hardest problem we will see. Okay, so let's take a look at the idea again. This is called delayed branching. And I'm going to give you a pipeline with two stages, instruction fetch and instruction execute. And I'm going to give you this code. These are instructions, A, B, C, and you have a branch conditional. C is dependent on A, and the branch conditional is dependent on C, but B is not dependent on any of these, as you can see. And then branch conditional, the target in the normal code is X over here, and the fall-through, which is the next instruction, which is D. Let's take a look at the timeline of execution here in a pipeline machine with two stages. And later we're going to look at the delayed branch code with a single delay slot. So I fetch instruction A. In the next cycle, I fetch instruction B. In the next, so you know how pipelining works. So in the next cycle, I fetch instruction C, and the older instruction gets out. And then in the next cycle, I fetch the branch conditional branch. Now at this point, I need to determine what to fetch. Assume that I don't have a branch predictor. I waste one cycle, clearly, right? Because the branch is not executed yet, and I determine what to fetch after the branch is executed. So I can fetch, in this case, G, assuming the branch is taken, only after I waste one cycle, right? So basically it takes 6 cycles to execute this code over here. And you know this, you know how to do this calculation really well. It's just a toy pipeline, in this case, two stages. So the idea of delayed branching is, in this case, to add one delay slot after the branch. And we're going to redefine the semantics of the branch to say that the instruction that comes right after the branch in code sequentially is always executed. The branch takes effect after one instruction. And now it's my job as the programmer or the compiler to figure out an instruction to fill the delay slot with. And luckily, I see that instruction here, right? If I look at this, I need to execute A, B, C, and B is before the branch. And B is independent of any of these, including the branch. So I can basically move B after the branch into the delay slot, right? And now this instruction is always executed regardless of whether the branch is taken or not taken. And I will keep the same semantics while getting better performance. Let's take a look at the execution of this. I fetch A. Clearly, I cannot move A or C because C is dependent on A, and the branch is dependent on C. So I cannot move C after the branch. It makes no sense because the branch needs the data flow coming out of C, right? There's a flow dependency here. But if there's no dependency, or if you can rename the registers at the compiler level or at the programmer level such that you get rid of the false dependencies, you can move B over here. So let's take a look at the execution of this code. I fetch A in the first cycle, C in the next cycle, and the branch in the next cycle. I don't have a branch prediction mechanism. That's okay. I'm going to fetch B in the next cycle, and I know that branch is not going to take effect at this point. I've redefined the branch such that I can execute B over here. And the branch takes effect in the next cycle. Now I jump to G, and I'm done. So basically, I've reduced the execution time by 1 cycle, which is a lot in a 2-stage pipeline. It's really 1 out of 6 improvement, right? And I don't need to have a branch prediction mechanism because I've just redefined the semantics of the branch. Yes? We'll get to that. So now you're thinking about the downsides of the mechanism. Yes, this works with 1 stage, but what if the branch takes 20 cycles to resolve, right? We'll get to that. Absolutely right. Okay, so it turns out if you have a single slot, even that single slot is not easy to fill before getting into the 20 stages. Let's take a look at an example, and things become more complicated. So this is good, but people introduced, Spark is another ISA that has delayed branching. MIPS is one of them. The early RISC ISAs, this is actually part of the RISC philosophy. The philosophy says, I want to minimize the hardware that I have in the machine, and I want to make everything the compiler's or the programmer's job, hopefully the compiler's job. You can think of this as part of that philosophy, right? The philosophy says, okay, why do I predict branches in hardware when the compiler can fill the pipeline slots with these independent instructions? Now let's take a look at another example. Delayed branch with squashing. Now what does this mean? We change the semantics slightly more. If the branch falls through, if it's not taken, then the delay slot instruction is not executed. So there's a particular delayed branch in Spark. People figured out that delayed branch slots are not easy to fill, so they added this instruction. Why could this help? Let's take a look at this example. We have ABC, branch conditional X. Now this is normal code. How do I fill the delay slot in this case? I cannot, right? Because assuming this is the only thing that you know, these are all dependent on each other and the branch is dependent on them. So you cannot move anything over here into the delay slot, clearly. So what do you do normally? Well, you put a no-op over there. If you have a machine with a delay slot, you put a no-op and you're back to square one. What does that mean? You are trying to fill the pipeline. You are filling the pipeline with a no operation, which is essentially useless, right? You're adding a bubble in the compiler level. Okay, so delayed branch with squashing gives you more freedom. You can now do this. Now, what is this? Essentially, this is the first iteration of the loop, ABC, and then branch conditional X. And then delayed branch with squashing says that if the branch is taken, the delay slot instruction is always executed. If the branch is not taken, there's hardware that squashes the delay slot instruction. If you put A, basically the A of the next iteration over here, it works. Because if you're going to take the branch, that's good. You're going to move something from the next iteration into the delay slot, and you're going to execute it. But if you're not going to take the branch, because you have this special instruction, the machine will flush that instruction if the branch is not taken. Of course, now this goes against the philosophy that we discussed, right? Now the hardware is doing something, getting rid of that instruction. We wanted to eliminate the branch prediction and flushing hardware, but now flushing hardware gets back in. Okay, so let's talk about the advantages and disadvantages of this. Clearly, this is a good idea if you can satisfy some conditions. It's an idea that can keep the pipeline full with useful instructions, assuming 2 conditions hold. One is the number of delay slots is equal to the number of instructions to keep the pipeline full before the branch resolves, right? So you need to determine this. And the second is also very important. All delay slots can be filled with useful instructions. This idea is useless if you're going to insert no-ops into the delay slots, right? Because you're not going to gain any performance with that no-ops. So this is very hard, it turns out. Second is very hard. It turns out the first one is also hard because how do you know what's the right number to assign to delay slots? Should it be 1? Should it be 2? Should it be 10? Should it be 50? Should it be 100? Does this delay slot remain constant over generations? Remember, this is the ISA. You're exposing this to the programmer, to the compiler. Compiler is going to write code assuming this. And if you change the number of, you cannot change the number of delay slots in the future, right? Because you're changing the interface. Everything above it will not work if you change the number of delay slots. But if you want to improve performance, you want to increase the pipeline depth, probably. So now you have a dilemma. You need to decide the delay slot, number of instructions over there, but you also want to change the pipeline depth. If you decide the delay slot is 1, and if you later add 5 stages to your pipeline, what do you do with the remaining 4 things that you need to bring into the pipeline? Well, the idea is to use branch prediction. That's essentially what all of these machines do, MIPS and Spark. They have delay slots, and the realization is that they shouldn't have done it. So basically, the first disadvantage is it's not easy to fill the delay slots, even with a 2-stage pipeline. Number of delay slots increase with the pipeline depth and superscalar execution width. And if you want to change any of those, now the delay slot doesn't help you. And number of delay slots also should be variable with variable latency operations. The real issue why this is a bad idea is it really ties ISA semantics with the hardware implementation. Basically, if you want to change the hardware implementation, the microarchitecture, to improve performance, the delay slot is a way of really overcoming the deficiencies in the microarchitecture, in pipelining. You shouldn't really have a mechanism in the ISA so tightly coupled with the implementation that you have. Because anytime you change the pipeline length and superscalar width, you'll need to increase the delay slot, which is not possible because that's exposed to the programmer. Okay, so we're going to pick up from here tomorrow. I'll see you tomorrow.